This is problem 16-19. When the two blocks A and B shown in the figure below are released from rest, block A, which weighs 500 pounds, slides up the inclined plane without tipping. If the kinetic coefficient of friction between block A and the inclined plane is 0.2, determine the maximum permissible weight for block B. Okay, so basically, we don't know how much block B weighs, but we do know it's going to be pulling down and causing block A to slide. Now, don't let the fact that block A is larger deceive you into thinking that a block A should be heavier. We have to go with the numbers in the analysis. So we do know what block A's weight is, and we are told what the kinetic coefficient of friction is between the block and the ramp. So we need to do a mathematical analysis in order to find out how the interactions will be with the forces using Newton's laws. So let's take a look at this. All right, so let's first start with a block diagram of block A. I'm going to barely tilt the block so that way we can see the 22-degree angle a little more obviously, and that'll hopefully help with the geometry. We know that the center of gravity is roughly here, and that the weight will be coming straight down. We were given that that weight is 500 pounds. And we now know, because of the ramp, that if we were to draw a straight line for the box, then that means that we'd have a 22-degree angle between the weight and that line on the box. The tension is coming straight perpendicular off the wall of the box. I'll call that T. We also have a normal force, which is going to be straight up the box, and there will be, again, a 22-degree angle with the vertical. And we'll call that normal force A. We also have a frictional force. Now, to choose which direction the frictional force goes, it really actually doesn't matter. But since we know the box is going to be moving to the right, that means the reaction force of the friction will be moving to the left. So we're pretty confident we'll get a positive number if we draw the arrow to the left. Again, when it comes to this normal force, I'm going to kind of jump right into the fact that this normal force is going to have some distance from the corner of the box. And typically in these problems where they're asking for the minimum or the maximum of something, they're implying that the normal force is actually going to be as far over to one side or the other of the object that is sliding. And so since the tension is the driver of the motion of block A, that means that the normal force is probably actually going to be all the way to the right on the corner of the box. And the box is about to start tipping, but just isn't going to quite tip, right? But again, to keep this kind of in an engineer's kind of way of thinking, you don't necessarily want to draw the normal force all the way in the corner. You want to talk about the fact that there is some unknown distance, but we are going to have to make an assumption that if the box is about the tip, that distance will be 0. This may not always be true in future problems. So now let's start doing the equations for the free body diagram, because I believe we have all the forces. So we will have the two sum of forces and then the sum of the moments. Well, as usual, we're going to have about G. And in this case, we could say X and Y, or we could say perpendicular and parallel to the ramp, something like that. Okay, so I'm just going to rotate my axes. So I'm going to say that Y is perpendicular to the ramp and X is parallel to the ramp. Okay, so that'll be some of the forces in the X, some of the forces in the Y. All right, and let's do the analysis. So some of the forces in the X are going to be the tension, which is positive, the friction, which is going to be negative. We'll also have the weight, which is going to be negative 500, and then it's the horizontal component, so sine 22 degrees, equal to the mass, which is 500 divided by the acceleration due to gravity, and then the acceleration of A moving horizontally, so acceleration in the X. All right, next is the sum of the forces in the y. You're going to have the normal force, so NA, and that's going to be positive. And then you're going to have the vertical component of the weight, which is going to be negative, so 500 cosine 22 degrees, and equal to 0 because the box is not expected to leave the platform or go into the ground. It's expected to slide exactly parallel to the ramp. All right, and then some of the moments about G. All right, we've got a normal force that is going to be a certain distance from the center of gravity. All right, this is where you could use the fact that there is a value d. Since we should use feet in this case, let's look at the dimensions of the box. So they told us that in the diagram that the box's width is 6 and 6 inches from side to center of gravity to the other side. They also told us that the center of gravity is 9 inches. All right, and the whole box is 18 inches tall. All right, and then just because we need to talk about this pretty soon, 14 inches high for the tension. All right, that means that as far as feet are concerned, the normal force can be half a foot minus the distance d. This is one way you could do this. Of course, we know that the box is about the tip, so the d is actually going to be 0. So that is where the half a foot is coming in. It's actually, this is a little bit confusing how I have this drawn, but you're starting with the normal force all the way in the corner, and then you add distance d, or you say that the normal force is half a foot away, and then you subtract away any value d that you happen to be moving to the left to bring the leftover amount of distance. That's actually a better way for me to be saying this. Hopefully you get what I'm trying to do here, and just know that this value is actually going to be 0. So that means that the normal force is actually, I'll just use a different color, is actually over here. All right, take a second to think about that if that wasn't immediately obvious what I was saying, or you can ask me during office hours. All right, next term is going to be the friction. Well, the friction is going to be 9 inches down from the center of gravity. The center of gravity is 9 inches above the bottom. That means that we are 0.75. So this is going to be plus the friction force A times 0.75. Now the force is going to cause a clockwise rotation, so this is actually a negative term. Next, an amount of space, so I'm going to come down here, is going to be the tension. So the tension times a distance of, well, we got 14 to the bottom, but we've got 9 coming up to the center of gravity, so that leaves us 5. So that's going to be 5 inches. Let's convert that to feet. Divide by 12. And the tension is pulling in the clockwise direction, so therefore a negative value. All right, and then equal to no rotation for the box, 0. How many unknowns do we have? We have 1, 2, 3, 4. And I believe that's the 4. But we only have 3 equations. Well, what are we going to do? Well, one thing we can do is that the frictional force is Fa equal to the mu Na. So that could be our 4th equation. So we should be able to solve for everything. The tension is going to be 389.4 pounds. The acceleration in the x direction is 7.045 feet per second squared. Our normal force is 463.6 pounds, not newtons. And then our frictional force is equal to 92.72 pounds. All right. But this doesn't actually answer our question. The question is that if the kinetic coefficient of the friction between block A and the inclined plane is 0.2, determine the maximum permissible weight of the block. Something's a little off here. Okay, so I have to point something out to you that first, let's draw the free body diagram of this block. So we have our tension, and then we have our weight. Now, we are being asked what the weight is going to be, so we actually don't know. So it could be the mass times the gravity, the acceleration due to gravity. Okay, well, this tension is equal to the tension on the other rope. So this is a term that is actually mathematically and physically connected. And we really, in this free body diagram, then are only adding one new unknown. So that's helpful. And let's look. So we know the block is only going to move in the y direction. So some of the forces of block B in the y. So actually, I should specify there are block A, block A, block A. Now, if we are to write this equation, then we would get that the tension minus the mass of B and 32.2, okay, for the acceleration due to gravity, and then equal to the mass of B, again unknown, times the acceleration of B. Okay, so now, what is the acceleration of B? Well, I was actually being misleading with this acceleration in the x, that we technically actually didn't know the acceleration in the x just yet, because the momentum of this block is actually a factor here. So if you try to solve for this, you may not actually get the right answer. Okay? And this is not obvious. This is somewhat confusing. This is tricky. And so we were making an assumption about D. So I'm being really, really tricky here. And I hope that this is more of a benefit than a problem. And that this whole concept of D being 0, because the block is B is pulling on A just to the point where it doesn't quite rotate, only is allowed to be done when block B is in the system. So I was actually not allowed to make D 0 yet, which means that, and I jumped the gun on giving you these answers. These answers actually wouldn't have worked. They are ultimately the correct answers, okay? But technically, D, this was technically an unsolvable system. Technically, D was another unknown, okay? So we got the tension, the friction, the acceleration, the normal, and D. And then, so that's 5 unknowns, all right? We actually only have 4 equations. D is only known when we add the block that is actually pulling the maximum amount allowed before the box A starts to tip over. That is not incredibly obvious. So what does this do? This gives us 5 equations, and then this gives us an extra equation with an extra unknown, actually with 2 extra unknowns, okay? The mass and this acceleration B. All right, so let's try to keep track of what's going on here. I have added in technically 2 more unknowns, the mass of B and the acceleration of B. But, and this is a big but, the blocks are connected to each other by a string. And so the speed at which B moves is going to be the speed at which A slides. So that's also meaning that the acceleration of A and B are coupled together. So AX of block A is equal to the negative AB of block B. Why negative? Because AX is moving to the right and block B is moving down, and we usually have down be negative. Okay, so that means that AB is negative AX. So now AB is technically not a new unknown. Well, what about mass B? Yes, mass B is a new unknown. That still puts us at too many unknowns, except now we're allowed to make D 0. So D has become known because block B's scenario has finally been met of the block B's weight is causing the motion of block A. That was probably very confusing, and I was being a bit misleading here in the beginning by giving you the answers, but these are the actual answers. And in fact, we now can also solve for the mass of B, which is equal to 15.48. By the way, that's slugs. That's the imperial version of mass. Okay, and then that means that the weight of B is equal to the mass times gravity, which is 499 pounds.